Start of Slide 1. Slide Caption. Chapter 7. Solenoids. Section 7-1. Electromagnets. Section 7-2. Solenoids. Section 7-3. Solenoid characteristics. Section 7-4. Solenoid applications. Section 7-5. Troubleshooting solenoids. End of Slide 1. Start of Slide 2. Slide Caption. Objectives. Section 7-1. Electromagnets. By the end of this PowerPoint, you should be able to define electromagnet and explain the left-hand rule. State the main characteristics of electromagnets. End of Slide 2. Start of Slide 3. Slide Caption. The left-hand rule states that if the fingers of the left hand are wrapped in the direction of the current flow in a coil, the left thumb points to the magnetic north pole of the coil. See Figure 7-1. An electromagnet consists of an iron core inserted into a coil. The iron core concentrates the lines of force produced by the coil. With the core in place and the coil energized, the polarity of the magnet can be determined using the left-hand rule. End of Slide 3. Start of Slide 4. Slide Caption. 7-1. Checkpoint. Does the added iron core of an electromagnet increase or decrease the magnetic lines of force? In an electromagnet, what determines the strength of the magnetic field? What is the left-hand rule used to determine when the direction of current flow is known? End of Slide 4. Start of Slide 5. Slide Caption. Objectives. Section 7-2. Solenoids. By the end of this PowerPoint, you should be able to define solenoid and state the function of each part used to produce linear motion in a solenoid. Understand why solenoids are available in different operating configurations to meet different application requirements. Describe the construction of a solenoid. End of Slide 5.
Start of Slide 6. Slide Caption. The 5 solenoid configurations are clapper, bell crank, horizontal action, vertical action, and plunger solenoids. See Figure 7-2. Solenoids are configured in various ways for different applications and operating characteristics. End of Slide 6. Start of Slide 7. Slide Caption. In a plunger solenoid, a spring is used to move the rod a short distance from its center in the coil. The rod moves against the spring tension to recenter itself when the current is turned on. See Figure 7-3. A plunger solenoid contains only a movable iron cylinder, or rod. A movable iron rod placed within the electrical coil tends to equalize or align itself within the coil when current passes through the coil. The current causes the rod to center itself so that the rod ends line up with the ends of the solenoid if the rod and solenoid are of equal length. In a plunger solenoid, a spring is used to move the rod a short distance from its center in the coil. The rod moves against the spring tension to recenter itself in the coil when the current is turned on. The spring returns the rod to its off-center position when the current is turned off. The motion of the rod is used to operate any number of mechanical devices. End of Slide 7. Start of Slide 8. Slide Caption. In an alternating current solenoid, the magnetic assembly and armature consist of a number of thin pieces of metal laminated together. See Figure 7-4. Eddy current is unwanted current induced in the metal structure of a device due to the rate of change in the induced magnetic field. Strong eddy currents are generated in solid metal when used with alternating current. In alternating current solenoids, the magnetic assembly and armature consist of a number of thin pieces of metal laminated together. The thin pieces of metal reduce the eddy current produced in the metal. Eddy current is confined to each lamination, thus reducing the intensity of the magnetic effect and subsequent heat buildup. For direct current solenoids, a solid core is acceptable because the current is in one direction and continuous, therefore has no eddy currents to cause issues. End of Slide 8. Start of Slide 9. Slide Caption. A small air gap is left in the magnetic laminate assembly to break the magnetic field and allow the armature to drop away freely after being de-energized. See Figure 7-5. As the coil is de-energized, some magnetic lines of force, known as residual magnetism, are always retained and could be enough to hold the armature in the sealed position. To eliminate this possibility, a small air gap is always left between the armature and the magnetic laminate assembly to break the magnetic field and allow the armature to drop away freely when de-energized. End of slide 9. Start of slide 10. Slide caption: a shading coil sets up an auxiliary magnetic field that helps hold in the armature as the main coil magnetic field drops to zero in an alternating current circuit. See figure 7-6. A shading coil is a single turn of conducting material, normally copper or aluminum, mounted on the face of the magnetic laminate assembly or armature. End of slide 10.
Start of slide 11. Slide caption: 7-2. Checkpoint. What is the movable part of a solenoid called? Why are solenoid armatures laminated? Why is a shading coil added to the armature of a solenoid? End of slide 11. Start of slide 12. Slide caption: Objectives. Section 7-3. Solenoid characteristics. By the end of this PowerPoint, you should be able to state common problems such as inrush current that solenoids produce in the electrical system. Describe the solenoid selection methods. End of slide 12. Start of slide 13. Slide caption: the mechanical life of most coils is extended by encapsulating the coil in an epoxy resin or glass-reinforced alkyd material. See figure 7-7. Magnetic coils are normally constructed of many turns of insulated copper wire wound on a spool. In addition to increasing mechanical strength, these materials greatly increase the moisture resistance of the magnetic coil. Because magnetic coils are encapsulated and cannot be repaired, they must be replaced when they fail. End of slide 13. Start of slide 14. Slide caption: solenoid inrush current is approximately 6 to 10 times the sealed current. See figure 7-8. Solenoid coils draw more current when first energized than the amount that is required to keep them running. When the solenoid plunger is not centered within the coil, the inrush current can be about 6 to 10 times the coil current compared to when the plunger is centered in the coil. The centered position is also known as the sealed position. After the solenoid has been energized for some time, the coil becomes hot, causing the coil current to fall and stabilize at approximately 80% of its value when cold. The reason for such a high inrush current is that the basic opposition to current flow when a solenoid is energized is only the resistance of the copper coil. Upon energizing, however, the armature begins to move iron into the core of the coil. The large amount of iron in the magnetic circuit increases the magnetic opposition of the coil and decreases the current through the coil. This magnetic opposition is referred to as inductive reactance or total impedance. The heat produced by the coil further reduces current flow because the resistance of copper wire increases when hot, which limits some current flow. End of slide 14. Start of slide 15. Slide caption: manufacturers provide letter or number codes to indicate the solenoid mount. See figure 7-9. For example, an A solenoid is selected for a door latch application because the door latch application requires an end-mounting solenoid. End of slide 15.
Start of slide 16. Slide caption: manufacturers provide letter or number codes to indicate the voltages that are available for a given solenoid. See figure 7-10. For example, a 2-amp solenoid may be used for an application that requires a 115-volt coil. End of slide 16. Start of slide 17. Slide caption: 7-3. Checkpoint. What is the initial current draw of a solenoid called? What is the operating current of a solenoid called? If the voltage applied to a solenoid is higher than the rating of the solenoid, will the current draw increase or decrease? What is the number of times a solenoid can operate in a given time period, usually operations per minute, called? End of slide 17. Start of slide 18. Slide caption: Objectives. Section 7-4. Solenoid applications. By the end of this PowerPoint, you should be able to state the number of positions, number of ways, and type of actuator a directional control valve has. List the different types of systems and applications solenoids may be used for. End of slide 18. Start of slide 19. Slide caption: positions are the number of locations within the valve in which the spool can be placed to direct fluid through the valve. See figure 7-11. A manual directional control valve is placed in different positions to start, stop, or change the direction of fluid flow. A directional control valve normally has 2 or 3 positions. End of slide 19. Start of slide 20. Slide caption: a way is a flow path through a valve. See figure 7-12. Most directional control valves are either 2-way or 3-way valves. The number of ways required depends on the application. 2-way directional control valves have 2 main ports that allow or stop the flow of fluid. 2-way valves are used as shutoff, check, and quick exhaust valves. End of slide 20.
Start of slide 21. Slide caption: in an electrical control valve, the solenoid acts as the actuator. See figure 7-13. A manual directional control valve uses a handle to change the valve spool position. An electrical control valve uses an actuator to change the position of a valve spool. In an electrical control valve, the solenoid acts as the actuator. End of slide 21. Start of slide 22. Slide caption: in a refrigeration system, direct-acting 2-way valves may be constructed as normally open NO, where the valve is open when de-energized and closed when energized, or they may be constructed as normally closed NC, where the valve is closed when de-energized and open when energized. See figure 7-14. Direct-acting 2-way valves are commonly used in a refrigeration system. 2-way, shut-off, valves have 1 inlet and 1 outlet pipe connection. These units may be constructed as normally open, where the valve is open when de-energized and closed when energized, or they may be constructed as normally closed, where the valve is closed when de-energized and open when energized. End of slide 22. Start of slide 23. Slide caption: refrigeration systems may use different solenoids, such as liquid line solenoids and hot gas solenoids. See figure 7-15. A number of different solenoids may be used in a typical refrigeration system. The liquid line solenoid valves could be operated by 2-wire or 3-wire thermostats. The hot gas solenoid valve remains closed until the defrost cycle and then feeds the evaporator with hot gas for the defrost operation. End of slide 23. Start of slide 24. Slide caption: different solenoids are used for the safe operation of an oil-fired single-burner system. See figure 7-16. Solenoids may also be used in an oil-fired single-burner system. The solenoids are crucial in the startup and normal operating functions of the system. End of slide 24. Start of slide 25. Slide caption: solenoids are used for general-purpose applications, such as those in airplanes. See figure 7-17. In addition to commercial and industrial use, solenoids are used for general-purpose applications. Typical general-purpose applications include products such as printing calculators, cameras, and airplanes. End of slide 25.
Start of slide 26. Slide caption: pneumatic robots can be used to replicate human movement with the added advantage of being able to lift objects of almost any size and weight repeatedly. See figure 7-18. Industrial robots are used in all kinds of applications, from welding, painting, sorting, and assembling extremely small to extremely large parts. They can replicate human movement with the added advantage of being able to lift objects of almost any size or weight repeatedly in almost any type of environment. Industrial robots use fluid power, where fluids are defined as either hydraulic liquids, usually oils, or pneumatic gases, often ambient room air. These fluids are used in cylinders containing rods or rams for linear motion, or rotary actuators for circular or arc motion, and grippers to provide the required power in movement. The cylinders, rotary actuators, and grippers are controlled by electrical solenoid-operated valves. End of slide 26. Start of slide 27. Slide caption, 7-4. Checkpoint. What type of valve is used to direct the flow of fluid throughout a fluid power system? What is the number of locations within a valve in which a spool is placed to direct fluid through the valve? What is a flow path through a valve? What does an electrical control valve use to change the position of a valve spool? End of slide 27. Start of slide 28. Slide caption, Objectives. Section 7-5. Troubleshooting solenoids. By the end of this PowerPoint, you should be able to state how transients are caused and how they can be reduced within an electrical system. Describe the steps required when using a digital multimeter DMM to troubleshoot a solenoid within a system. End of slide 28. Start of slide 29. Slide caption, Manufacturer charts are used to help determine the cause of solenoid failure. See figure 7-19. Solenoids usually fail due to electrical problems or mechanical damage. Electrical problems include coil burnout, erratic operation, or an open fuse or circuit breaker. End of slide 29. Start of slide 30. Slide caption, the voltage applied to a solenoid should be plus or minus 10% of the solenoid rated value. See figure 7-20. The voltage is measured directly at the valve when the solenoid is energized. A DMM set to measure alternating current voltage is used for alternating current solenoids. A DMM set to measure direct current voltage is used for direct current solenoids. The range setting of the DMM must be greater than the applied voltage, or the meter will only display an overrange on its readout. End of slide 30.
Start of slide 31. Slide caption. A DMM set to measure voltage and resistance is required when troubleshooting a solenoid. See figure 7-21. To troubleshoot a solenoid, the following procedure is applied. 1. Turn off electrical power to solenoid or circuit. 2. Measure the voltage at the solenoid to ensure the power is off. 3. Remove the solenoid cover and visually inspect the solenoid. Look for a burnt coil, broken parts, or other problems. Replace the coil when burnt. Replace the broken parts when available. Replace the valve, contactor, starter, or solenoid-operated device when the parts are not available. Note: determine the fault before installing a new coil when a solenoid has failed due to a burnt or shorted coil. Coils will continue to burn out if the fault is not corrected. Always observe solenoid operation after a solenoid is replaced. 4. Disconnect the solenoid wires from the electrical circuit when no obvious problem is observed. See complete procedural list on pages 185 to 186. End of slide 31. Start of slide 32. Slide caption, 7-5. Checkpoint. What is the acceptable voltage range, high and low, that should be applied to a solenoid? What device is used to reduce transients produced by solenoids? What is the acceptable resistance range, high and low, that should be measured when testing a solenoid? End of slide 32. Start of slide 33. This is an audio pause for defining the different meanings of the very same words that are frequently used in electricity versus those same words used in fluid power systems, such as hydraulics and pneumatics. These words are open and closed. In electricity and electronics, the drawbridge analogy can help you remember what a circuit or device does to the electron current flow. When the drawbridge is open, there is no vehicle movement across the bridge to get to the other side. So, vehicle flow is shut off. But when the drawbridge is closed, it allows vehicle flow across the bridge, just like a closed switch would allow current to flow in a circuit. The definition of fluid power systems used with hydraulics and pneumatics employs the opposite meaning of the words, open and closed. Fluid systems use the barn door analogy to explain the status of the fluid flow pathway. When the barn door is open, the animals are free to move through the doorway. But when the barn door is closed, they cannot move through because it blocks their path. Think about it, and both technologies will make more sense when you hear those words, open, and closed, with opposite meanings applied to the charged particles flowing through electrical or electronic circuits, versus the liquids or gases flowing through hydraulic or pneumatic systems. End of clarification. Context-sensitive use of the words open and closed. End of slide 33. Copyrights originated by the publisher with modifications by Nita Layton and Glenn Graham.